When we think about computers and the devices that control and power our daily lives, we're really thinking about electronic sensors or control systems as they're also called. Now, control systems can be described using a block diagram, and this picture here shows the types of blocks that are available. The computing device you're on now takes your taps on your keyboard, processes that information, then displays the letters you want on the screen. There must be at least one of each type in a control system, but there are usually many. We're going to deal with each stage in order, so let's start with the sensing device. Sensing devices are transducers. So, what is the definition of a transducer? You should be familiar with that, so have a quick think back. How would you put it into words? So a transducer is a device that changes a non-electrical signal into an electrical signal, or vice versa. Here are some examples. We've got a thermistor, a light-dependent resistor, a strain gauge, and a piezoelectric crystal. The first two should be quite familiar to you, so we'll get those out of the way first in this video. In another lesson video, I'll cover the strain gauge, and then I'll also cover the piezoelectricity in general, so I can focus on them better. So, a good understanding of thermistors and LDRs relies on your knowledge of band gap theory. So it's well worth looking back at that, but here's a quick reminder. The valence band is full, which means charge cannot flow there. Even if electrons moved around freely, the net charge would stay constant at its maximum value because it's full. The conduction band has space in it though, so when electrons move from one atom to another, the total charge in those atoms changes, and that's current flow. In a metal, the valence bands and conduction bands overlap, so there is a good supply of electrons that can move around. In an insulator, there's a big band gap between the two bands. Electrons can't get from the valence band up to the conduction band, so charge can't flow. Semiconductors have a small band gap. Normal things like room temperature might provide enough energy for some electrons to jump across the gap and provide a flow of charge. Or we could use doping to provide exactly the number of electrons in the conduction band that we want. The important thing for us here is that providing energy increases conductivity. For some materials, this energy can be provided as light. This is an LDR. More light means more energy, which means more conductivity, which means lower resistance. For some materials, this energy can be provided as heat. This is a thermistor. More heat means more energy, which means more conductivity, so lower resistance. Now, you may have heard about negative temperature coefficient thermistors and positive temperature coefficient thermistors. You are familiar with the first type, the negative temperature coefficient. And that's the one you need to be able to explain, just like I have just done. The other type is more like a change of state. It actually behaves in a similar way, but then switches and flips. You're better off ignoring that for now. We learn about the negative temperature coefficient thermistor because it relates to band theory, so it has a nice synoptic feel to it. So that's an introduction to electronic sensors and a couple of the sensing devices, the thermistor and the LDR. We've still got a couple to come up, looking at the strain gauge and looking at piezoelectric crystals. And then after that, we're going to get on to the main part of this topic, which is the processing device as well.